Okay, good morning everyone. Today I'm going to continue on where I left off on Tuesday, talking about the evolution of high efficiency silicon solar cell design. As I mentioned, I'm with the new Australian Centre for Advanced Photovoltaics, and this is the first public airing of its new logo. So this is what I'm going to go over, but I'll start off recapping some of what I mentioned last week and then start talking about some of the principles underlying the high efficiency design itself. So this is what I mentioned last week. By the early 60s, cell technology had evolved to this stage, and there was a standard design, 2 centimetre by 2 centimetres, actually 6 fingers that you can see here. And for about a decade, this was the way solar cells were made. So no one deviated from that because the types of missions, this is the first space mission, but the types of missions were very critical that nothing go wrong, so stuck with the standard cell design. So as I mentioned, it had a problem in that it had a very heavy diffusion. So this is phosphorus versus depth. So you notice 1 micron is a long way for these impurities to diffuse into the silicon material. So this doped region near the surface is very shallow, considering that the wafer is several hundred microns thick. So it's only the top % or so of the device that is actually doped, even though a lot of these drawings, the regions are looking pretty similar in size. Also, these lateral dimensions are very much larger than the vertical ones. So these fingers, as I think we elucidated on Tuesday, are a couple hundred microns wide and spaced several millimetres apart. So 6 of them over 2 centimetres goes 3.3, I guess, millimetres apart in the standard design. And then came the violet cell. So in the early 70s, people started reassessing the cell design with all the advances that happened in microelectronics. So photographic techniques were used to define these contacts, went from 6 fingers to 8 and then to 12. So a big leap forward. This cell was known as the violet cell, which started getting the efficiency moving up again, this point here, about 15% efficient under terrestrial sunlight. So the things that were done, and we'll talk more about this in the next phase of the lecture, a lighter diffusion here to get rid of that dead layer I mentioned that formed at the surface. And then photographic techniques were used to define these fingers so they could be made much narrower, put closer together, and this reduced the resistance penalty from going to a lighter diffusion in this region here. This doped region near the rear, by heating an aluminium layer on the silicon rear, you could actually get it to cause the silicon to melt at quite low temperature, and then when it re-solidified, it was doped with aluminium, which is a P-type dopant in silicon. Higher index anti-reflection coating, the ones we used before were a little bit low, and as I mentioned last week, it was also less absorbing material. So silicon monoxide used to be used, and titanium dioxide, tantalum pentoxide, and a range of other less absorbing anti-reflection coatings started to be used. And because the cell could now respond better to blue light, because there was no dead layer along the surface, the anti-reflection coating was sensible to make it thinner, because the cell previously couldn't respond to blue light, so you designed the anti-reflection coating for longer wavelengths, but now that you could respond to blue, it was more sensible to have a thinner anti-reflection coating, and the cells sort of look violet, so that's why they're known as the violet cells. And then this substrate was more heavily doped. So increasing the majority carrier concentration reduces the minority carrier concentration. So the NP product at thermal equilibrium is a constant. So push up the doping, you push down the minority carriers. And as we mentioned last week, current flows are due to gradients in minority carriers. So if you push down the minority carrier concentration, gradients are going to be smaller and current flows are going to be smaller. So we'll talk a little bit more about that as well. The next big step forward, and it was quite a jump as you can see, in 1974, which is when I joined the university here, this cell was reported the black cell because it looked like black velvet when you looked at it. But the major advance over this one was the use of this texturing of the surface to reduce reflection. So I think the reflection technique, reduction technique is quite obvious, like light coming down will first strike one of the sides of these pyramids, and most of it will be refracted into the silicon material. But what isn't reflected, refracted in is reflected, but the angles are such that it has to get reflected downwards. So that means it has at least 2 chances of getting coupled into the silicon. And if you think about it, if you've got 10% reflection on your first loss, if you have 2 bounces, you get 10% of 10% loss after the second bounce. So you can reduce a cell with 10% reflection down to a cell with 1% reflection by that technique. So it's a very good technique for getting very broadband anti-reflection properties. And it's used in most commercial cells. Speaking of which, this is my standard diagram for what a commercial cell looks like today. It's quite an old version. These finger widths have steadily come down as the technology has improved. But basically, the cells that are sold commercially now are black cells. So they're using the technology that was pretty well known in 1974. And what's going to happen over the coming years is a lot of the improvements that I'll talk about, that we demonstrate in the laboratory subsequently to this, will be what happens in commercial production. So what I'm telling you is going to be very relevant to what you see in commercial production over the coming years. So this is a standard commercial cell. The main difference is between this and a black cell is the way the contacts have been put on. Some of the improvements I'll talk about soon, have already been incorporated into these. So a couple of years ago, they were about 17% efficient as well. Now some of these getting up to 18, high 18s, 19% efficiency, higher than the laboratory cells that were sort of their prototypes. So this is the way the metal contact is applied commercially. You just have this screen and the metal is sort of ground up into a paste, mixed up with other stuff, so that it's a thickish type paste. And then it's just squeezed through this screen onto the cell to give you the defined patterns. The other technique I was talking about last lecture used a similar type of mask to this, but the metal was just sort of evaporated down here so that it just got through where the holes were, whereas this is more of a physical process where you push the paste through the mask. So this screen printing process works very well, and that's why cell technology has been stagnant commercially for quite a while, because this screen printing is a really nice process that works quite well, and it's been improved quite a bit over recent years. Okay, just looking a bit more detail at the cells I've talked about now. This was a conventional cell, 60s to 70s, that was ruled. So the open circuit voltage was about 550 millivolts. Going to the violet and black cell, went to more heavily doped substrates, and that increased the voltage to close to 600 millivolts. Now that's pretty pathetic by present standards, so most commercial cells will have 620, 630 millivolts voltage these days. So that was an obvious deficiency in the performance of the device, the low voltage, but people were struggling to find ways of increasing it. Big boost in the current. So most of this boost is the removal of the dead layer and the improved anti-reflection coatings. So that gives most of this boost, and then the better reflection in the black cell gives the additional current boost. And these are the spectral responses that I'll skip over for the moment. So I want to talk about 3 different principles tonight of increasing sophistication. The first one is the superposition principle that I think most of you will be already familiar with. But as I mentioned last week, here's Walter Schottky again, who developed a lot of this theory. You can treat the light and dark currents within a cell separately. So that's really good. So I'll be talking about what happens in a PN junction in the dark and everything, and you might ask how relevant is that to a solar cell that works in the light. Because of this principle of superposition, you can separate the 2 out. So to design a good solar cell, you want to have a good dark characteristic here. In particular, you want this bit of the curve to be pushed out as far as you can in this direction. So this in microelectronics, this is called the knee voltage of the diode, where the current starts increasing. So you want a high knee voltage. And to get that, you can do things like dope the substrate more heavily. So that's what's done with diodes. So you want to suppress all the dark currents in a solar cell. So you want to push this curve out as far as you can. All this light generated current is determined by generally other design parameters of the cell. So you can sort of optimize the voltage, this open circuit voltage, and the current separately. At least that's what we thought, but I'll show it's a little bit more interrelated than that. So this principle of superposition, it applies pretty well. You've really got to look for examples where it doesn't apply. More or less it implies for most cells. Series resistance is the main cause of departure because series resistance effects are different in the dark from when illuminated. Is there a clock anywhere? Oh, thanks. What I'm going to talk about now is the emitter design. And you probably all know, but this is the emitter of the cell, the top thin diffused region near the surface. And this is our termination originated with Walter here because a lot of this technology development was originally done for his NPN transistor shown here. So this was the emitter. It emitted the carriers within the PN junction transistor. This was the collector over here that collected them, and this middle region was called the base. So that terminology is sort of carried over into solar cells. So this is always called the emitter, what's it emit, but that's the emitter and this is the base. So what I'm going to talk about now is the effect of these surfaces, because the first thing we did when trying to improve that black cell design was start looking at the surfaces and how they influence cell performance and how we could reduce that influence. So I'm going to start looking at the surface of the emitter. So next bit, improving emitters. So just to recap, this is from the red book, but this just shows the carrier concentrations under a dark PN junction diode under forward bias. And as I said, that's relevant to a solar cell because everything gets superimposed. So this is a linear scale here. The carriers that spill over from either side when you forward bias the junction decay exponentially in their respective regions, as shown here. So this is what happens if the regions go on for infinite extent. This will decay back to the equilibrium value. If you go to heavier doping, like this side is heavier doped than this side in this case, you can suppress. This drawing's not all that good. This should actually be bigger than this. This drawing's more representative here, but the proportionate increase here is smaller than the proportionate increase in this case. So going to heavy doping sort of suppresses how high this concentration gets. The current flows depend on the gradient here. So dndx, if you call x this direction, minus dndx, determines how many electrons flow in that direction there. There's a constant, the diffusivity, d, that determines how much flow you get for a given gradient. Okay. We'll just blow up that left-hand side. So this is just blowing up the p-type side in that previous diagram, and this is the exponential decay down to the thermal equilibrium value. So you're causing a disturbance by forward biasing the diode, particularly in the regions near the junctions, and that disturbance just decays as you move through the device. So all pretty straightforward. So what happens if there's a surface in the right way? So you stick a surface like that. And it depends very much on the properties of the surface. So if you have a really bad surface, if you scratch the surface with sandpaper or something, you can get a really bad surface. And that gives you what's called an infinite surface recombination velocity. Any minority carrier getting that surface is instantly gobbled up. So it means that you can't maintain an excess of them. If there's any carriers there above this equilibrium value, if there's any excess above that, they just get gobbled up and infinitely quickly if you've got an infinite recombination rate. So what's that do? You can see that, wow, you've increased the gradient here. So you're getting more current associated with that. So that dark knee voltage is moving in, so that's going the wrong direction. So you don't want infinite surface recombination velocity if you want a high open circuit voltage solar cell. And remembering that as the design was evolving, this thickness here was reducing. So going from the conventional space cell to the violet cell, this thickness was substantially reduced. If you go the other direction, if you have a perfect surface, if you have a surface that's inert for minority carriers, you have what's called a zero surface recombination velocity. It doesn't matter how many carriers get to that surface, they're just not going to recombine. There's no process for them available there to recombine. And what happens there is you get an enhancement of the carrier concentration throughout this region here. And you'll note the gradient here is reduced very substantially. So very much less, like it might be 5 or 10 times less in this drawing here. But that means 5 or 10 times less current flow, so your knee voltage can increase accordingly. It turns out a 10 times decrease in current flows I'm talking about, corresponds to a 60 millivolts increase in open circuit voltage. So if you've got a solar cell with 600 millivolts open circuit voltage, a 60 millivolt improvement is quite substantial. So this is the type of thing you can get by controlling the surface recombination velocity, like a 10% supercharging of the cell performance. If you have the value of the surface recombination velocity just right, and in this case it's equal to this diffusivity I mentioned divided by the diffusion length, that decay constant here. So if it has that particular value, you don't change anything. The carriers get to the surface and it just looks like to them as if the material continued on indefinitely. So that's the critical bit in deciding whether, that's the critical value in deciding you get behavior like this or behavior like that. Okay, now comes something really interesting. When we did this work, we were thinking about the effects upon voltage primarily. Our initial aim was to improve the voltage of the cells above that 600 millivolts. And when we started this work, I think 620 millivolts was the record, the world record for the highest voltage that had ever been obtained from silicon. So our initial aim was to try and push up that voltage to much higher values. And this was the type of thinking that governed that work. If we go back to the conventional cell, it had this dead layer at the surface. So this was more like what happened in the conventional space cell. You had this dead layer where there was just no chance of minority carriers surviving. They just got suppressed to their thermal equilibrium value, but that increases the gradient further, as you can see there. So you've wiped out this region of the cell by doping it too heavily, and that increases the current flows to that region, which reduces voltage. Okay, so what I'm going to talk about now is a principle not too many people in the photovoltaic area know about. So if you understand what I'm talking about here, you'll be ahead of, I reckon, 95% of the people that think about these things in the solar area. But it's a reciprocal relation between the dark properties of the cell and the light properties. This is a diagram from my red book. I didn't know about this relationship when I did this work, and if I hadn't known about it, it would have made everything a bit simpler, I think. But if you look at my red book, I've got a exercise, or I guess it's a theoretical development that I do there. And I don't think I hadn't seen it done before that time, but I assume there's this is an unphysical situation, although you might be able to think of ways of getting it experimentally, but you assume you've got a plane within the cell, and I've done it on the thick base region of the cell because that's wider, less influence from surfaces. But you've just got so this is the generation rate of carriers. You've got none, then an impulse function of generation right at that point. So that turns out to be quite a simple situation to analyse, which is why I did it in the textbook. But that's figure 8.1. Figure 8.3 has the solution. So this is the probability a carrier is generated, distance x from the junction is collected by the junction or contributes to the short circuit current of the cell. So if you generate right in the junction, that's great. The carrier's got a good chance of getting collected. There's some situation you've got really bad material that won't occur, but practical silicon solar cells, 100% of carriers generated in the depletion region get collected. And then you get these exponential decays on either side. If I had been a bit more astute then, we said, wow, that looks pretty much like the decays of the whole of the minority carrier concentrations we saw in some of those earlier overheads. And in fact, it turns out that that's the case. There's a relationship between this decay here and the distribution. This is for a device that's illuminated. There's a relationship between this collection probability and the distributions you get in the device in the dark. So, there's no way you could have guessed that or anything. There's no physical argument that you could make that would show that relationship, but it just happens. It's a fundamental relationship due to the nature of the differential equations that govern everything. So it's a property of the mathematics involved in formulating these solutions. But that's, you can go one step further. You can look at the effect of finite widths of these regions, and these exponentials get modified, as we saw for the case of the carrier distributions. And I even go to the trouble in the textbook of giving the solutions there. Again, if I had have given the solutions for the carrier concentrations, I might have noticed the connection. But if we go back to this diagram here, it turns out, like now we're talking about the carrier distributions throughout the device, but they're exactly equal to the probability that if you generate a carrier at this plane here, for example, like just a concrete example, if you had a plane of generation here and you had an infinite surface recombination velocity, the ratio of this to the value here would give the probability of collection. So, we didn't know that at the time, so we were sort of thinking the current and voltage in the cell are sort of separate, but they're fundamentally linked by this relationship. So, like if you look halfway across here, this will have, about half the value that it does at the junction, so that gives you a 50% probability of collection of carriers, which is about right, because this is acting as a sink for carriers. If you short circuit of a junction, that means there's no excess carriers there, so that'll act as a sink. So the sink here and the sink here just battle for the carriers, and you have a 50% chance of collection. However, if you do something that's good for the voltage and try and reduce the surface recombination velocity, you can see that you bump up the probability of collection of the carriers as well. So, doodling with these little diagrams of carrier distributions in the dark, gives you a lot of information about what's happening in the cell. I might add, this is for the case of uniform doping. It gets a little bit more complex if the doping is non-uniform, but the same principle applies. So these expressions here that were derived for the carrier collection probability, given in the red book, actually describe these carrier concentrations in these two limiting cases as well. So, if the diffusion length is reasonably small, this won't be quite a straight line. It'll bow down a little bit from a straight line and be described by that relationship there. So that's something that if you understood that, you know that a lot of people working in photovoltaics don't know. So you're ahead of many of them. Okay, now getting back to the technology side of things, I'll talk about how we applied all this in improving the cell design. This is the chart of efficiency versus time, and we started making a contribution in 1983. This was our first world record for silicon cell efficiency. But what we did to try and control the surface recombination velocity, we were trying to fix up the emitter of the cell first. So we said we got to get that S close to zero as we can. It turns out a native oxide on silicon is a really good way of neutralizing the electronic activity of a silicon surface. Like that had been known for decades, and that's why silicon, was so successful in microelectronics. This native oxide, or the oxide that forms if you heat silicon and oxygen, it really forms a very good interface with silicon, and that was underpinned the microelectronics industry for decades. It's moved on from that now, but that was the reason it got to where it is now. So we initially put oxide along the surface, even under the metal contacts. So metal to silicon forms an infinite recombination velocity contact. So that's really bad news. Wherever you have a metal contact to silicon, S equals infinity, and you get all those linear gradients and extra current flow, etc. By putting this oxide under there, we could make that look less damaging to the minority carriers, that region. So this was the structure that gave us our first world record in 1983. So mainly it was a S reduction both along this surface and here. It turns out, having, like we've got a metal here and then an insulator and then semiconductor, you say, well, you mightn't get any current flow there because you've got an insulator, but we had to make these oxide regions very thin here so the carriers could flow through that insulator by quantum mechanical tunneling. So that's one of the successes of the quantum mechanics developed in the 1920s was, it predicted current electrons could flow through regions that were classically forbidden, and going through an insulator is a region that's classically forbidden, but if it's thin enough, the electrons can get through there. So it had to be about 2 nanometers, 20 angstroms for that to occur. In this region here, we could have the oxide thicker, but you ran into different problems. If the silicon index is very high, it's about 3.5 relative refractive index. That of oxide is about 1.4, 1.5. So it turns out optically you want a gradation in index going from silicon to air to get the lowest possible reflection. So having a low index layer, in the stack isn't a good idea. So these anti-reflection coating materials that we chose were progressively, we had a double layer coating, so we had one layer that was high index, zinc sulfide, which is quite a high index, and then another layer of magnesium fluoride to try and grade the index of silicon down to air. Having this oxide in the way wrecks the optical design, but if you keep it very much smaller than a wavelength, the light doesn't really see it. So here we had different constraints on how thick we could make the oxide. So it was about 3 times thicker than in this region, just keeping it so it didn't influence the optics. So that structure, and you'll notice we have no texturing, it's just a planar device structure, but we're still able to beat the black cell efficiency record. So essentially what we're doing by this approach is we're just reducing the flows of carriers both in this region here across to the contacts, across to the surface. So you can regard this as sort of a lot of one-dimensional things all together in parallel, but there's flows to the surface here of holes. That's going to be reduced if you have a good interface here. And then the flow to the contact is reduced by having this oxide layer here. So you get improvement both in contacted areas and non-contacted areas with this approach. Oops, I think I skipped one there. Yep, I did. The following year, we simplified the structure a bit and got better performance. So often making things simpler allows you to get better performance, less exacting, less demanding to make the devices, and you can pump them through more quickly, and simplification of what you're doing is always a good idea. So what we did here, we retained this oxide here, so its thickness, as I said, was determined by optical constraints. But instead of having the oxide underneath the metal, we used a different strategy to reduce the influence of those contacts. We made the contact region very small. So what we have now is we have good surfaces all along here, but bad surfaces right in the contacted areas. But if you reduce the contact area, so as I said, this isn't drawn to scale. This width of this region here in our devices was probably about 2 microns. The depth of this region here was about 4.4 of a micron. So these contacts are actually, spread much over. If I drew it to scale, you'd have them spread over a much larger thickness than this. So they'd go, about the extent of this thing here. So it's nearly a geometrical thing. You've got regions where you've got enhanced current flows to the contacts here, but you've kept the total flow down by keeping those regions small. So that was a different way to improve emitter properties. And again, most of our improvement came through improved voltages in these structures. Better move on. The next big jump was by introducing texturing. So all those little pyramids that in a standard approach don't work well. Well, we had trouble making them work with the photographic approaches that we're using to define a lot of the features here. So we worked with more controlled structures. In this case, we worked with what we called slats or microgrooves. So these are formed by the same crystal planes in the silicon, have the same angles and everything, but we just confine them to I guess it's a 2-dimensional structure rather than a 3-dimensional. And that got us to the first 20% efficient silicon solar cell. So that was a real milestone, because back when the first cells were developed, which, particularly in the 1950s, where there's a lot of excitement and that front page headlines on the New York Times and everything, people started trying to work out what was the efficiency limit on a silicon cell, and a lot of people came up with 20%. That was about the best you could do. So that was like the 4-minute mile in athletics, a bound that could be sought but probably never attained. So this was a real milestone, achieving the first 20% efficient cell, and there's a very happy group here that did achieve it. So you might recognise some of the faces. This is Stuart Wenham, who was my number 3 PhD student. Andy Blakers, who was number 2 PhD student. He's now head of a group similar to ours at ANU. Chi-Man, who's here at the back, he was number 8 PhD student, Chi-Man. Mohan was number 5, Zhao was number 6. But all these people have gone on to do great things within the industry. So this is just where some of them have ended up. So Jiman's here, of course, working with technology transfer. Mohan's been CTO of a number of the major solar companies, including Trina, and now CTO of Hanwha Solar One. Ted here, he has been he's probably done the most work in terms of getting the industry to where it is now. He established the production lines at 2 of the major solar cell manufacturers, Suntech and JA Solar, as well as a couple of other ones that are in the top 20. And so on. Zhao is Vice President of Technology at China Sunergy. So everyone's gone on to do something interesting in the solar area. Okay, next topic I'd like to talk about is light trapping. So we had some questions on it last week. This is Eli Yubanovich, who did the most interesting work with light trapping, although Adolf Gertzberger had sort of thinking of the same ideas at a similar time. But light trapping relies on the fact that the index of silicon is very much higher than that of air. So 3.5 times that of air, approximately. So you might remember back to your physics, there's total internal reflection if you have light traveling in high index materials. So if you get light into a silicon, if this was just a flat reflector, which is what people had been, well, what they use in space cells is flat reflectors on the back, any light reflected from that rear reflector just bounces straight back out again, just follows the same optical path. But if you do something to roughen the rear surface or something or other, you can get the light sort of reflected off in other directions. And if it's reflected within the escape cone of the silicon, it'll go straight back out. So the escape cone of silicon lies within about 16 degrees of the surface, in a range of about 6, I think it's 8 degrees half angle. So if it's reflected within that half angle, it will, at this angle here, is small enough, it'll just go out of the device, getting refracted this way when it hits the air interface. However, if it's reflected at a little more oblique angle, it gets totally internally reflected at the surface. And total internal reflection is like 100% efficient process. Unless you have dust or something on the surface of the device that can help couple the light out. But if you had nice pristine surfaces, total internal reflection is effectively 100% reflector. So you can't do too much better than that. So Eli developed the theory of what are known as ergodic light trapping schemes, which means schemes that randomize the direction of light, sort of evenly over all angles. So that's just completely randomizing the light as random as it can get. And he showed that the light trapping, if this was a thickness W, by using a randomizing reflector here, you could increase the optical path length in that material by a factor of 4n squared. So as I said, n is very high. The refractive index for silicon is 3.5. So if you figure out 4n squared, you get something like 50. So by doing something like this, you can increase the path length 50 times over that of a single pass across that layer. So that's quite an important boost. If you've got a solar cell that's 300 microns thick and you multiply that by 50, it's something like, 1.5 centimeters. That's sort of the absorption depth that you're working with. So it's really quite a substantial improvement in terms of trapping light within the device. We were interested in these schemes that were based more on geometrical structures, and we thought we could probably do better than that because, like randomizing things is like not using your engineering skills. We were engineers, so we said, we can engineer something better than randomizing stuff. So we tried to see if using these geometrical features we could get better than that. And Patrick Campbell, who's still within the group, and myself worked out that you could get even better than 50 times. You could get a lot better than 50 times. But you had to pay a penalty, which is what I mentioned last week. If you restrict the range of angles that you're willing to accept light from, and that mightn't be all that silly to do, you can correspondingly increase your path length. So, as shown here, so 50s is just like a lower limit. since then there's been an integral form of this equation developed. So if you have a variable angular sensitivity of a cell, you can now derive what the path-linked enhancement would be. So that sort of established the baseline. I might add these are all for very thick cells, much thicker than a wavelength, and there's been a lot of recent work on what happens when the cell thickness is small compared to a wavelength. Can you get enhancements beyond this? And the answer is not in the average case, but in some extreme cases, yes, very, very much so. So that's what's meant by light trapping, and it's a function of the high index of silicon. You know, one way of, no, I won't go into that, won't have time. So we started to think about that, incorporating that into our designs around this stage. So that led to the second era of cell design. Most of the work we'd been doing up to then was based on fixing up the emitter, like the front surface of the cell. The back of the cell was pretty standard. But then our run of efficiency records, we got our 20% and then pushing beyond just refining what we were doing. And then this group at Stanford University interrupted our run of records with this structure here, which was a double-sided cell structure. It's quite unusual. This is one of their drawings, but the sunlight comes from this direction here. I always used to point out, you know, being in the southern hemisphere, the sunlight sort of comes from on top here rather than from underneath. But this structure here, you know, it's quite interesting. You just got a silicon wafer and all the actions on the back of the cell. So this is the rear junction cell, is probably the correct terminology for it. It's got both the N-type junction and the P-type. Where is that? It seems to have dropped off this drawing. Oh, it's underneath these regions here. So you can't see it in this drawing, but there's a little P-type doped wells here. So all your P-N junction activity is on the rear. It turns out you need very good material for this structure to work, because most of your carriers are getting generated near this surface. They've got to find their way over to this rear surface to work. So you need very long diffusion lengths for the structure to work and very low surface recombination velocity along these surfaces. So it's quite a demanding structure, but it sort of pushed the technology in the direction of going to more sophisticated approaches. So this is what the commercial cell looks like, drawn it the right way up this time. You know, all the action on the rear. So if you look at one of these cells on the front, it's just black velvet. There's nothing there apart from this texturing and an anti-reflection coating, so virtually non-reflective surface. And then on the rear, there's all this action. There's metal contacts, you know, running the length of the cell and so on. So all the action's confined to the rear. So that raised the stakes. We then started to look at what we call double-sided structure. So we've been working on the emitter. Now we have to look holistically at the whole cell structure. And this is the device that ultimately resulted from that, which we call our Pearl cell. Passivated emitter, you know, we've done all the work on the emitter, rear locally diffused. So we went to this idea of just having you know, rear contacts in selected areas similar to what the Stanford group had used. So that's the Pearl cell structure. So we used all the tricks that we found for the, that we used in our 20% efficient cell. We've gone to a more sophisticated texturing approach, sort of a 3D approach. And this one was chosen and designed to maximize the light trapping in the device. So we incorporate features into the exact patterning and so on that enhance the amount of light that get trapped in, and we get quite close to that 50 times trapping of the light within the material. Wherever we made contact to the device, we took one extra step. We did a heavy diffusion, which was what was used in the Stanford structure. Oh gee, I'm going to run out of time. So you remember, this is P-type, this is P+. The electron concentration has to be lower in the P+ compared to the P. You know, but the product in thermal equilibrium, you know, the NP product is constant. So this P being high means N has to be low. So what doping in the contact region does, it suppresses the carrier concentration in that region, suppresses the minority carrier, and so that's going to suppress all those gradients to the contact. So you know, that's a way of reducing the contact recombination. So we've incorporated that in the front side, so wherever we have a metal contact, we have it sort of protected by this heavily doped region that stops the minority carriers from getting there, and then apply it to the rear as well. And then we use oxide enshroudment to passivate the whole surface. An additional refinement here is that we use the electrostatic effect of this rear contact to control the recombination in this intermediate region here. But I won't have time to go into that. Okay, moving on. Another reciprocal relationship I'll just briefly touch upon. What I want to talk about is the Shockley-Quasar limit on efficiency. So this shows the limiting efficiency for a single junction cell versus the band gap. And in 1961, I think, Shockley and Quasar derived a limiting theory that would apply for any single junction solar cell. And this is it shown here. These are a lot of experimental results for different cell technologies, including a 25% crystalline silicon device. But Shockley and Quasar looked at the case where the only recombination processes within the device were radiative. So in our silicon devices, you get a lot of radiation like this, defects in the material, so you get recombination occurring through defects. And this Auger process becomes very critical if you manage to reduce this. This radiative process is quite interesting in that the extra energy of the electron that's released when the recombination event occurs causes a photon. And that photon has energy above the band gap of silicon, of the material that it's occurring in. So it can be reabsorbed within the material somewhere else. In these processes, you lose the carrier, you've lost it. In this process, the sort of carrier sort of lives on in the form of this photon. So the photon can bounce around in the device and it's not necessarily dead. But that makes it very complicated to analyze what's happening in the device, and people had sort of struggled with that. Black body radiation, I hope you're familiar with this. This is just the energy distribution from the sun versus wavelength. Very similar to a black body radiation. You get this wavelength distribution that peaks at particular wavelengths depending upon the temperature of the black body. I'll just go over this and probably skip over the rest because this is quite important. Fundamental theory that describes what the limits on cell performance, what really determines them. But Shockley and Quasar did quite an elegant analysis. They said, we've got a solar cell here. We want to work out what the limiting open circuit voltage in particular of that structure is. The current's quite easy to calculate. You know how many photons are coming in. If each gives you a carrier, you've worked out the current. But what determines the voltage? So they said, if this device, assuming it was a black solar cell and had good anti-reflection coating and textured surface or whatever, if it was just sitting in the room, like this room, at room temperature, how much light would be emitting? And if you remember back to Kirchhoff's law, you can work that out. A black body emits radiation characteristics of its temperature. So you can work out exactly how much radiation this solar cell is emitting at room temperature, sitting in the dark. If you then apply a voltage to the device, what happens? Oh, well, going back one step, if you look at the strongest optical processes within the structure, at the energies corresponding to the band gap of silicon, these are these absorption processes across the band gap. So there's nothing else that comes close to matching that in terms of the strength of the process. So if you look at the black body that's being emitted by this solar cell sitting here in the room without any voltage or light shining on it, most of that radiation that's being emitted at energies around the band gap is occurring from these radiative recombination and regeneration processes backwards and forwards across the band gap. So automatically taking into account all these photon recycling and total internal reflection effects that really complicate analysis looking from the inside out, looking from the outside in simplifies things down enormously. So if you then apply a voltage, we know from what I've said before, all the carrier concentrations increase exponentially throughout the device structure. And if you've got good surfaces, they increase just about uniformly throughout the device structure. In fact, if you want to collect all the photocarriers, they have to increase uniformly throughout the device structure. So what will be the total recombination in the device in the dark with a given voltage across it? It's just going to be that black body radiation that lies at energies above this band gap here, exponentially enhanced by the voltage. So this is the expression here. Yeah, this is the radiation from the sun multiplied by multiplied by the at 6,000 Kelvin, which is the sun's temperature approximately. And this is the, if you like, the radiation being emitted by the the cell. It's the black body radiation that's above the band gap. This integral is just done above the band gap for both, exponentially enhanced by this factor here, which is the factor that increases the carrier concentration through the device. So you can work out the limiting efficiency of a solar cell just by looking at black body radiation characteristics. And that's what Shockley and Quasar did. Looking at experimental devices, like this is black body emission. This is the black body spectrum at 300 Kelvin. I showed it for the sun before. So this is the photons per square metre per something or other up here. So this is the number of photons being emitted by a black body, you know, one of our solar cells sitting here at room temperature. So you, and this is wavelength, so 10 microns here. This is the visible region here, which we can have a closer look at. The visible region here, you know, you won't see much radiation from the device. You know, I can see you now, not because you're emitting radiation, but because radiation's getting reflected from you. So the eyes aren't responsive to this region that these bodies are emitting. But if you look at where silicon's band gap is, on this scale you start getting this little bit of radiation emitted. So this amount of radiation here determines the amount of recombination within the device that's above the band gap at, you know, without any voltage there. And if you increase the voltage, this just gets exponentially enhanced. If you look at one of our solar cells, and this is a radiation emit, it turns out that it's, you know, this is wavelength here. It turns out it's similar to one of those little blips. It gets refined a bit because, you know, because of some of the details involved, but it's pretty much the same. So the solar cells actually do behave in that Shockley-Quasar mode. But one very important relationship that I'll just mention, but it's important, it's fairly new. Like again, I'd say 99% of the people working in the field are not aware of this relationship, so if you cotton on to what's being said, you know, you'll be ahead of most of the people. But it turns out that solar cells don't emit quite as much as that exponentially enhanced black body radiation. Only a perfect solar cell will do that. And Uvarao found just, you know, a few years ago that the actual expression for the amount of light emitted by a solar cell was the black body term multiplied by something that we're perhaps familiar with, the EQE of the cell acting as a photovoltaic device. So again, sort of a coupling of different types of applications. This is sort of an LED type of application. You're looking at light emitted, but it depends on a parameter that's, you know, that's relevant to a device operating as a light detector. So, you know, quite an interesting relationship. So this is our, this is the EQE, which is just the number of electrons you get in the circuit per incident photon. This is the EQE of one of our 25% efficient cells. Very good across most of the visible spectrum, drops off at the band gap, and this fall off here determines the shape of this curve. Very important relationship. Some of the members of our team have developed commercial equipment based on that now can inspect silicon cells looking at the light emission. So this is showing a multicrystalline cell, and the pattern you get is showing you the EQE variation over the cell surface, or the quality of the cell over as it varies spatially. So very handy tool, diagnostic tool. Final bit, just talk about the future. I'll just have to skip some of this. Some of the cell designs that people are looking at, like within the group here, we're working on laser doped selective emitter structures where we automatically, we get away from that screening printing process, automatically align the contacts to regions that were heavily doped using lasers to provide that patterning. That's another structure. Subtech, being our most prominent licensee, had a lot of these cells in production, although that has scaled back a bit over recent years. The other cell you might have heard about is a HIT cell structure, uses higher band gap material, in this case hydrogen doped amorphous silicon, which has a higher band gap than the normal silicon to form the emitter and the base contact. Emitter wrap through cells, a lot of interest in other approaches to getting rear contacts apart from the sun power approach. So having little holes through the wafers that brings the contact through. Or you can bring the whole metal pattern through the contact as well. So that's the metal wrap through cell. So looking further ahead into the future, where do I see things heading? It turns out that the thermodynamic limit on solar conversion is not 25%, better stop, but 74% for global sunlight, sunlight coming from the whole sky. Lots of approaches have been suggested for getting from a single cell limit, the Shockley quasar limit, up to that 74%. But the best way of doing it is stacking cells on top of each other. And it turns out that silicon's not a bad choice for the bottom cell in the stack. Like if you stack 2 cells on top of silicon, this is your limiting efficiency with the silicon as the bottom cell compared to an unconstrained choice. So pretty good choice as the bottom cell. So this is where I think things might be going. Actually finding techniques for growing thin film cells. Thin film cells are very good quality on top of silicon to sort of supercharge the performance of the device, taking the limiting efficiency, you know, from 30%, which holds for present devices, to something like 50% for a 2 or 3 cell stack. So I better finish there, but thanks for your attention.